Welcome everyone to the second day of the workshop. So I hope you had a wonderful day yesterday in the speed, especially the speed dating part. Right. So the first talk is going to be given by Professor Patrick Charbonneau. Okay. So he's going to tell us about random Lorentz gas.
Okay, good morning, everyone. Thank you very much for showing up, for finishing your coffee on time. And also, but most importantly, thank you so much to the organizers. It's a real honor and a pleasure to be here. I don't know how this talk will go, but in the worst case scenario, I get a wonderful view. So I'm at peace with this. So I'm going to be presenting work that I've been doing over the last few years, but I being understood here in a very broad sense, meaning that it was mostly the work of postdocs and students and collaborators, in particular Gianpaolo Folena, Yi Hu, Peter Morse, Mingwan Zhang, that were at Duke at various times, and Dmitro Komenko and Griffin Alfaro Miranda were in Rome at various times as well. I'm going to be talking about active matter, which from a mathematical perspective or a theoretical physics perspective in the language of this sequence, but I'm going to introduce it in a very strange way, in a way that actually I would advise my students never to do. I'm going to start by talking about a model. Okay, it's a really bad idea in general.
That's not bad.
Only Gérard can get away with it normally, right? I don't have that heft. So here's my model. It's called the random Lorentz gas. And for those of you who've never encountered it, it's a very simple model, right? And I have a sketch of it on the left, which I think is correct. So what I have is in this case, spherical obstacles distributed at random. So Poissonian distribution, so uniform over space. The obstacles, which are the gray disks, don't interact. They can overlap. They can be really anywhere. And I have a tracer, which is a point, a pure point. And in this case, it follows a ballistic trajectory. So it will go in straight line up until it collides with obstacles and has a specular reflection, and will go like this. And you can, if you are bored, this is obeys periodic boundary conditions. You can try to trace the course of this tracer through space. So at low density obstacles, this is what it would look like. If you make it a much higher density system, you start having interesting structures to these trajectories, right? So for instance, in this one is a quite high density. You have clusters of trajectories. So space, the void space being explored by the tracer, and you can see the density of the trajectory sort of building up throughout it. So it's a work it's an image by Franosh. So it's a model. So it's actually a quite old model. It makes an allusion in a sense to Lorentz model of 1905. Lorentz model was for periodic obstacles, so it's not actually his model per se. That's why it's called the random Lorentz gas. It's been a classic of kinetic theory in the 60s. It was quite popular as a model for percolation and localization in the 1980s, and since over the last 20 years, or last 15 years, undergone some sort of revival as a model for reactive and active transport, a bit what I'm going to be talking to you about today, but also about localization and dynamical arrests, and about jamming most recently, right? So it's very versatile. The simplicity of this model, a bit like the universality of the random landscapes or the random functions that Joe was presenting yesterday, endows it with a very broad range of applicability. And one of the things I really like about this model is that it simplifies many things, right? So the reasons why theoretical physics likes models in general. But it's not only that it makes things simple, it also pinpoints where the true fundamental difficulties are. Right? So it looks so simple. Whatever you can, wash away, what's left is actually quite difficult and reveals something sometimes quite profound about the nature of the phenomena you're looking at, even though it's a one particle with non-interacting obstacles taking place. So one of the things that makes the revival of this model particularly interesting in the context of this sequence is that it obeys what we'd call a spin glass-like description, meaning that in infinite dimension. So if I take this model with a dimension of space, in the meaning that Danielle meant it yesterday, right? If I take the dimension of space, go to infinity, it happens to have the exact same mean field description, or the exact same description as hard spheres. right? So if I look at these two models in finite dimensions, they're very different, right? I have my hard spheres there. I have multi-particle correlations. All these pairs are interacting. And same thing, my random Lorentz gas is very different because it has just one tracer interacting with different obstacles that are not themselves interacting. But if I take the dimension of space, go to infinity, I can show that they have the exact same partition function and the exact same dynamics up to a factor of 2, right? There's a trivial scaling factor, it's a factor of 2, but everything else maps exactly. So I can actually learn a lot about, and for those of you who don't know, the description of hard spheres and limit of infinite dimension is very much akin to that of spin glasses. Slightly different equations, but the overall very similar structure with the dynamical transition, to make a cartoon of what Gérard was presenting yesterday, right? So you have a low density phase, that is your liquid. So if I have a low density of obstacle, or if I have a low density of hard spheres, I have some sort of large ergodic component that encompasses most of phase space. And this is what I present in my liquid. If I go beyond this dynamical transition, or the clustering transition, right? I have these clusters of phase space that take place. Sorry. Oh, which is very fun. I have these clusters of phase space where the system can evolve. And dynamically, this would correspond at low densities to having a system. If I look, let's say, the mean square displacement, at long times it will be diffusing. If I'm at low density, if I'm at high density, at long time, I'll be plateauing. I have an Edwards-Anderson order parameter that describes the size of these clusters, the size of these non-ergodic regions that develop. So I have a transition around the dynamical transition from one regime to the other. Right? So this is
Sharp transition. It's not just regime.
In infinity, it's a sharp transition. Right? In any other context, it's their regimes. Okay, so an example of this, right? How useful is this insight into understanding the behavior of the random Lorentz gas? So I can look at the dynamical mean field theory of hard spheres in infinite dimension, or the mean field if I look at static quantities. So in this plot on the left here, so I'm going to start by looking at the liquid side. The plot on the left, I look at the mean square displacement of the random Lorentz gas as function of time. The dashed line is the DMFT solutions, and the colored lines are the numerical simulations, so literally integrating the equations of motion of the random Lorentz gas in different dimensions, 3, 6, 12, and 24. And you can see that as I increase dimension, I very quickly converge to the DMFT expressions at low densities, at high densities. I can look at a deviation from the DMFT predictions, actually, and the corrections are of a shape of 1 over D. Right? So
how do you choose the density of those balls?
Wisely. No, so you take the asymptotic scaling for these quantities, the high D scaling of these quantities, so they remain of order 1. So
you're looking as a function of density.
So these are for different densities, so different dashed line correspond to different densities, and the different colors correspond to different dimensions at these densities, right? So I need to take...
There's no temperature because it's hard sphere.
Yeah.
Yeah, okay.
Exactly.
It's only density.
It's only density. It's trivially described by density. In this case, the density is the density of obstacles, right, that I have in my system. So this is what happens to the DMFT. If I look at the localized phase, I have I can look at the order, the Edwards-Anderson order parameter, and it also, so the dashed line here is the mean field theory prediction, infinite D, and these are finite dimensional results, and in this case, 2, 3, 4, 5, 6, and 7D. And here again, I have a 1 over D correction to these. So there's a quantitative agreement between the DMFT, or the mean field theory, with perturbative 1 over D corrections all the way to 3D for much of the density regimes I'm considering.
I mean, except at the critical point.
Thank you.
What was the comment?
Except at the critical point. So let's look at one quantity that diverges at the critical point. So if I look, for instance, at the distribution of cage sizes. So I'm looking at the fluctuation of cage sizes here, and there's 2 types of fluctuations that can be taken into account. There's one that's just about, let's say, the shape of the cages or the size of the cages. So I have a heterogeneity in the distribution of these cages. And then there's also a thermal heterogeneity. Depending on where I start in the cage at initial time, that will give me a different contribution. And yes.
How do we quantify anything about the cages? What's on the y?
It's some sort of variance of the mean square displacement. So it's some fourth moment of the distribution of displacement properly normalized.
I guess I don't understand when you're saying when it works well, when you said before there wasn't a transition except in infinite D.
Yeah.
So at long times it's wrong.
Yes.
But this is if you look.
But if I look at low densities and look at high densities, there's great agreement. Around the transition, obviously, things are complicated. In one way in which it's complicated is that you have a diverging susceptibility, right? And the susceptibility diverges in infinity.
High density, the long time and limit doesn't commute with looking at this local structure, right? So the long time limit is associated with large length scales.
So if I have high enough densities, the limits can be exchanged, right? These are static calculations looking at long times. It's infinite time because, I mean, geometrically, I have a cage that is geometrically fixed. There's no rearrangement taking place. In the random Lorentz gas, you don't have any potential rearrangements.
Consistency. This is really with the Lorentz. Okay.
Yes.
I misunderstood.
Yes. It's a random Lorentz gas. Right.
Really.
Small fluctuations around, looking at small fluctuations around the dynamical mean field theory. So beyond the D goes to infinity description, right? Looking at the level of fluctuations in caging. And, okay, and, you know, why is Pierre Francesco right? But if you start looking at what happens as you approach a transition, things get to be a bit messier. I'll get to that in a minute. But at least if you stay away from the transition, there's very good agreement. Again, 1/d correction to these results. Yes.
Is caging a technical term, or do you mean?
No, this is a literal
what is a
cage.
cage exactly?
I have obstacles. Fixed obstacles, and I have a tracer that's exploring phase space, and they cannot escape.
So there's trapped forever?
They're trapped forever.
But so the difference is that somehow the number of these cages where it's trapped forever, which can exist in any dimension, is exponentially small in one phase and order 1 in the other phase.
Mm-hmm.
Yeah. Okay.
I mean, so yes. Yes. I mean, I do have a complexity that develops, right? The complexity is related to the fact that I have multiple caging environments that
in
develop.
any density in any dimension, because there's some probability.
There's always a property to having a small cage, but they're probability 1, they don't.
So is it that if you start at a random position, you don't diffuse below the transition, and if you're above the transition, you do diffuse at long times from a random initial condition?
Yes. Yes. Yes.
How is the density of the point scaling with the dimension of the obstacles? Are you keeping it literally constant?
The density? No, it's not. No, everything is scaled. It's 2 to the D times phi over D, right? There's a proper scaling. It has your scaling. Yes.
Okay, great, thanks.
Yeah. It depends what you define as a diameter, but yes.
Just for clarification, so you draw the spheres overlapping here, right? So they can overlap.
The obstacles can overlap. Absolutely. I mean, it's a random Lorentz gas. These obstacles don't see each other.
Okay.
Now, it turns out if I want to look at the fluctuations of the dynamics, I don't have an analytical prediction for this. We don't know the deviations, the small fluctuations around the DMFT from first principles, but I can compute numerical results and check their, I mean, I have an expected scaling for these, and actually I have a quantity that corresponds to those. It's what's called the non-Gaussian parameter. So it's a measure of how non-Gaussian is the distribution of displacement as a function of time. And it has a peak around the regime where I go from ballistic to diffuse, or when I go to the cage escape, rather, right? So at short time of Maxwell-Boltzmann distribution, I have a collision timescale, I have a caging timescale, I have an escape, and then the diffusive timescale. And the maximal heterogeneity, or the peak of this function is maximal around the cage escape regime. And here what I'm showing is alpha 2 is function of different densities, right? So I can see that the peak grows as I go closer and closer to this dynamical transition that is expected. Yes.
Sorry, what is alpha 2?
The non-Gaussian parameter. Again, a fourth moment over the second moment normalized such that it's 0 for Gaussian distribution. Okay. And you can see, so I can do this in pretty high dimensions, so I can really see a nice growth. And if I look in the liquid phase and I collapse them, I get a dimensional dependence that's very weak again, something like 1/d in the corrections and the fluctuations. So it's a reasonably well-controlled model. and a challenge in a sense for theory in the regimes where we have simulation results and the theory is not yet matched us, at least away from the transition, right? As you expect. So one of the conclusions also for this, you might be wondering, how can I get something that gets so strongly correlated even though I have a single particle? What you end up correlating is the dimensions along which you're displacing. Right? So the number of dimension grows, so you're able to correlate displacement along an increasing number of dimensions, which is what allows this peak to grow, even though I have just one particle exploring. It has one particle with d dimensions. So obviously, in finite d, this will plateau at some point. In infinite d, it can grow unbounded, as you'd expect for this. This is a signature, if you want, of an avoided phase transition in finite d.
But if you, so I guess maybe but one is one of these quantities related to the fraction of initial conditions that diffuse?
Sorry?
Is one of these quantities related to the fraction of initial conditions that diffuse?
Not yet.
What is that? Oh, okay.
That's coming. Yes. Okay. And I'm happy about all the questions you've had, but maybe one confounding point that you may have raised already is that it says, honestly, this is a quite technical talk. It's quite dry. But nevertheless, a thought came to me. Didn't you say that the random Lorentz gas is a model for percolation? How can it be a model for percolation and for glass formation at the same time? And to put this a bit more concretely, right? This is the infinite dimensional description of the Edwards-Anderson order parameter as function of density, right? So if I go to very high density, this cage size goes to be very, very small. And if I shrink this density, it grows up until it reaches the dynamical transition where this continuously jumps from a finite number to infinite, right? So that's I go from being localized to being completely delocalized over all space. But if this is a problem if this is a model of percolation is not a discontinuous transition. It's a continuous transition, right? If I look at my percolating clusters here, so the colored regions in my series of obstacle, this volume or this mean square displacement that characterizes this, and these clusters grow and diverges continuously at a percolation transition. And then it's infinite at low densities. Right? So how can there's a physical or mathematical inconsistency in these two descriptions. One of them says I should go discontinuously at least in infinite d, right? Should go discontinuously. But same thing for the percolation. I mean, the percolation universality description does not change actually in the limit of.
There are some costs of percolation that.
Not this one.
Continuous.
This is a very simple standard percolation class. So how can the two be related? And the answer is that they're not. Actually, both phenomenologies take place in the random Lorentz gas. They're different, distinct transitions. So the red line here is actually the percolation transitions worked out numerically. This is a more la la land world. This is a wild extrapolation. We don't actually know how it scales in the limit of infinite dimension, right? But numerically, we can determine this with pretty high accuracy. And the dynamical transition, if you believe, if you want to extrapolate it or keep it as a crossover in finite d, it would be around 2.4 in these units. And clearly, the two transitions don't follow each other. They actually cross around d equals 8. So if I go to high enough dimension, actually, I have a triangle here where I first encounter this imperfect caging transition that is mean field-like or Neko mean field-like. But I'm not really caged because I'm only really caged once I hit the percolation transition. Right? So in between here, something fun must be happening, right? Because I have two types of caging, one imperfect and then one perfect, purely geometrical once I go beyond it. Okay. And what's this resolution to this, right? If you think about these long time limits and the probability of escape, actually, if you look at the dynamics, the probability of escape in this regime, it has an instantonic type character. What do I mean by this? I mean that the probability of escape scales like e to the minus some constant times the dimension times the gap in density between the avoided transition and the density at which you are, with surely higher order corrections, but numerically this is what we can determine. And you can see that so depending on how far above, so 2.5 would be slightly above this line, 2.7 a bit further, 3 a bit further, right? You can see these instantonic escapes get more and more suppressed as you increase density, as you'd expect. Okay, so
I'm
yes.
confused, but it seems there's two interpretations of this naively. One is that most initial conditions don't diffuse, and a very small fraction of them do diffuse. And the other is that most initial conditions, or substantial fraction of initial conditions, diffuse but very slowly.
So in this case, we can actually geometrically determine whether you're caged or not. So we can compute the fraction. So what happens? I mean, both of them happen. You can be perfectly caged, and it's a fraction of them that escapes, and some of them are just rare escape paths, right? Rare entropic bottlenecks that you can go through, right? So this is a potential reconciliation of these two types of physics in the same model, right, that we're proposing, but again, remain beyond analytical or mathematical control because like we don't understand the interaction. We don't understand even the percolation transition limit of infinite dimension for the void percolation problem. Okay. Now you may be still wondering, like, okay, this is fine. You resolved my first concern, but didn't you read the name of the conference? It's called Spin Glass Theory and High Dimensional Landscapes in Biology. Where's the biology? So, okay, let me bring in the biology now. And to do this, I'm going to introduce what are called active Brownian particles. What are active Brownian particles? Well, a Brownian particle would just be a particle that's diffusing with some diffusion coefficient and some random noise. And I'm adding some persistent velocity, right? And then I need to let this vector here diffuse. I have a rotational diffusion that will allow this vector to shift. And then I can control how big that persistence is relative to the Brownian motion, the passive Brownian motion, by we call it a Peclet number, a type of a ratio between the velocity and the diffusion coefficients. Right. So this is a model that's been studied quite some bit in the last 15 years. It has some interesting physics as function of the Peclet number and the volume fraction here, the packing fraction. Just a lot of these particles. So if I'm here, I have my passive Brownian particle. All I have is a liquid, and eventually I'll get stuck because I'm a high density, something like a glass type arrest. But if I turn on the activity, I have what's called a mobility-induced phase separation that develops. So I have something that looks like a gas-liquid coexistence, but in a system that has no attraction whatsoever. So this is an example of what would develop as function of time in this MIPS regime. So I start with a homogeneous system, and then clusters grow and develop. And there's lots of ink that's been or bits that have been spent on describing and studying this particular transition and this regime. So one of the beautiful features of this. The key thing, this is a model that's biologically inspired, actually is deemed to be a pretty good model for a variety of microorganisms, in particular non-tumbling microorganisms such as certain mutants of E. coli. So
what is the x-axis in this graph?
the density. So this is phi, this is volume fraction. Sorry. Got cut in my copy and paste exercise. Okay, so if I now take my random Lorentz gas not to be a Newtonian particle, but a Brownian one, and I can choose it to be passive Brownian, what I call Brownian particle, simple Brown particle, or active Brownian particle, and I look at its behavior in a cage, right, of obstacles, again, overlapping at a fairly high density, I have qualitatively something quite different, right? So if I look at the behavior, the color actually shows a time evolution from time 0 to 30 in some relevant units, right? But I can see, right, the passive Brownian particle does exactly what you'd expect. It's exploring the volume roughly uniformly. I mean, I need to run it for a longer time to actually get a proper uniform sampling, but it's exploring the bulk and the surfaces and everything else. And it can find these rare escape routes, these entropic bottlenecks once in a while. My active particle, however, does not sample space uniformly at random, right? It actually prefers to spend a lot of time at the surface of the obstacles and can get stuck. You know, if you have narrow edges, then you can spend a lot of time diffusing out, trying to find the way out of this regime. And it seems to have actually quite an easy time finding entropic bottlenecks because it's surfing the surface, right? The fact that it's narrow doesn't actually impact it that much, actually much less than a Brownian particle. I mean, one way to quantify how much it gets to be interacting with the surface is by looking at the simple pair correlation function, right? In the case of a Brownian particle, this is a simple step function, go to 1 because it's a trivial pair of correlations. I only do not penetrate obstacles. If I'm an active Brownian particle, I now have a lot of time spent at the surface. So I have a really large peak at contact, and the larger the activity, the higher this peak. And this is not particularly new in terms of effective attraction, even though we don't have solutions to the outer equilibrium equations, right? We have the equations, but we don't know how to numerically solve them. We can nevertheless study their low density behavior, and you can find there's actually an equivalence between a Fokker-Planck and a DMFT descriptions of these systems, where you can give an effective attraction that describes this extended time living at the surface. So it's not a surprise. Yes.
When you have this active thing, so you have a velocity v0 somewhere, then there must be some obstacles where v0 pushes in the wrong direction.
And what is the wrong direction?
The one that doesn't allow you to exit. If you have an exit here and it pushes this way, then this will be a trap.
Yep.
Yes. It's not always good, as you know.
No. Actually, yes, you're right. You might be stuck. I mean, if it were infinitely persistent, if you find one edge, you'll forever stay there.
You know, for instance,
so there's an interplay between the distribution of these wedges and the activity. It's not.
You know, mathematically, this has been understood in the much simpler context. If you take supercritical percolation cluster with the drift, then there is a regime where when the drift is strong, you have very slow dynamics. Yeah. Even though you are supercritical and you can always go.
Okay.
But because there are some of the traps where V0 pushes in that direction and then stucks you there.
Okay.
So it's very similar to that thing.
Yeah, okay, good. Okay, I didn't know. That'll be interesting.
Yeah, but that definitely depends on there being a systematic bias in one direction.
Yeah.
Flow, right? Because it's the two exponentials beating each other. But it's not clear if, I mean, people can't do some of the large deviation things here to try to identify what the problematic.
No, they can't even do the mean field version of the dynamics. So let alone the large deviation.
Well, but sometimes you can do large deviations when you can't do mean field.
Okay, well, you know my name. Look up the number.
But it's true that it started for this percolation thing.
No, it's interesting.
Which correspond to the.
We should talk about this. So this, I looked at showed you a static picture. I can look at the mean square displacement. This is a reminder of what happens to a passive Brownian particle. The active Brown particle, I don't have analytical prediction for what goes on in infinite D, but I do have a steady convergence. So different colors here correspond to different densities. And at least at low density and a high density, I do converge to, I seem to be converging to a master curve that should be the analytical prediction if we were able to compute it. If we look at what happens to the avoided dynamical arrest, right? If I do some sort of power law fit around in the vicinity of dynamical arrest, I find that this dynamical arrest actually shifts to higher and higher density. At least it seems to saturate. It cannot go beyond the percolation threshold, right? Geometrically, it cannot. So it seems to actually plateau towards the percolation threshold in the particular density dimension where we did this simulation. So that's an interesting. But what's more interesting in the sense that in the previous description I showed you these cage escapes in this intermediate space between the dynamical arrest and the percolation threshold were sort of activated like, they were instantonic like, but they no longer look instantonic, right? Activity somehow transforms these instantons into easily fluidizable escape pathways, right? The same geometry, right? But somehow things that were hard, exponentially suppressed, now become quite easy. And for sure, there's an interplay of the Piclet number and this feature that I don't understand, right? But that would be nice to do so. Now, if I go back to the fluctuations, again, as a reminder, this is my non-Gaussian parameter. And in my cage escape, I have a peak that grows. This is the results in 24D I showed you earlier. If I looked at the active version, I also have a growing peak in the cage escape. So it's consistent with heterogeneity in caging and heterogeneity developing in this regime. But I also have a new peak. Yes.
Why do you say that regions that were exponentially suppressed that you cannot observe, you can observe? I mean, this algorithm is out of equilibrium. So
Sure.
of course I can crunch the system and I can explore higher densities. So
Yeah.
that's how it's works.
Yeah. I mean, but so okay. So I don't know how to describe this. I mean, in a static, in a passive case, these are exponentially rare. If I change the dynamics, obviously I can change the sampling. I do change the sampling of these regions. So maybe I should not be surprised, but it nevertheless happens.
Yeah, I mean, it's just that the algorithm is driven into regions that are not typical from the point of view of the Edwards measure, but I mean, you can go there.
Yeah.
They can exist.
Absolutely.
So can you just say again what the rules are? The definition of the active one? It always has a probability of rotating around.
Yeah.
Time.
Yes. Yes. So I can tune how big V0 is, or the diffusion, how that compares to the rotational diffusion. So I choose the rotational diffusion to scale with dimension in a reasonable way as well, so it doesn't vanish.
So on sort of large time scales, it's in the same class. So if there's a transition in with the normal Brownian.
Geometrically, yes. If there's an escape path, both should find it. They just find it with way different eases.
If I just take a long straight channel, then it doesn't keep going down that channel, right? It goes down some typical distance and then turns around.
Yes.
So it can't, the sort of natural kinds of traps don't trap it. Well, no, because if they make it thinner and thinner, the channel, then it takes longer and longer before it turns around.
No, the turnaround actually will be the same, dependent of the width. But the difference between the active and the passive one will become increasingly large as you make the channel vanish. Right? Because before we can talk about this, let me finish my talk, please, because I'm told you want to break. Foolish. Now the other thing that arises in the active Brownian case is a second peak, not at time that grows with the caging time, but actually at a finite time, and grows with density nevertheless and intensity. And actually, if we try to map it, it grows only with density, but it grows with dimension. So if I look at the peak height as function of density, so it always exists. There's always a maximum as function of density, but also the peak height grows. So this suggests that there's a signature of the fact that I move to the surface and I start exploring the surface, but it's not the surface that I'm exploring. It's objects of codimension one. Right? So the higher the density, the lower the space that I actually explore. Because it's not the surface, it's the intersection between two spheres and the edge that will grow. And this edge will be ever smaller dimension, and these wedges become points while the bulk is still D. Right? So I have a signature of this localization at the surface or at these low dimensional features that give rise to this unexpected criticality that should be present also in infinity. Okay, which brings me to some perspectives, right? So first, active particles explore low dimensional features of cages before cages are even fully defined, resulting in short time D goes to infinity criticality without standard glass equivalent, which is a completely new physics. Active particles explore low dimensional passages associated with activated entropic bottlenecks in passive glasses. This is what we've been discussing in the last few minutes, right? So this is maybe not surprising once you know it, but not something that was particularly well discussed before. The high persistence limit should correspond to a trap model in which traps, the vertices in this case, are connected by cage edges.
What is it? Persistence?
The persistence, the Peclet number. Okay. So the high Peclet number should correspond to a trap model, right? Where I'm exploring. And then you can imagine like an even simpler model that it would be maybe easier to track. It's be an active Brownian particle in a random polyhedron. Right, where I have a distribution of edges and a distribution of vertices and vertices angles. And this is something that presumably one should be able to solve with enough stochastic geometry and a bit of sweat on the computers to figure out. Okay. All this to say that there's much to learn about what we normally call many-body physics in a single one-particle model, which I think is quite nice. And brings me to my last slide, which is my wish list. Right, at heart a numerical person. I do some theory and I work with some of my best friends are theorists, as we say. But there's still some open questions that I wish me or my theory friends or mathematical friends could resolve, including how to solve the out-of-equilibrium DMFT for the active Brownian particle, for instance. That would be a very simple example. How to solve small fluctuations around out-of-equilibrium DMFT, also an open problem. The large fluctuations, obviously, a very important question in disordered systems, and in particular in this DMFT. And from a purely geometrical standpoint, right, understanding and putting all of this into context would be really helpful if we actually understood the asymptotic threshold for verb perturbation. And with this, I'd like to thank you for your attention. So, do I get to choose who asks the questions, or you choose? Yeah. She allows you.
Okay. I'm wondering if you have actually had a chance to study the magnetic Lorentz gas model. To the best of my knowledge, there's analytical results for it. You probably introduce some no-Markovian memory effects. It's not quite your active thing, but sorry if you mentioned it and I missed
No, I did not, and it would make it non-reciprocal.
Chirality also,
right? Yeah.
right?
It'd bring us closer if I did.
That would be
I agree. It's one very good reason to do it, but I have not done it yet. Thanks. Yes.
So one of the most important phenomena in these active Brownian particles is this mobility-induced phase separation, right? So do you have any analog of that in the one-particle system?
No, you don't. It is a one-particle system. It is limited, and the obstacles are fixed. So, I mean, the analog would be to be infinitely trapped on, or to have this long persistent caging in a, but it's really more of a glass analog than it is a MIPS. So, yeah, Francesco. No, okay. Daniel.
Can I, if I make just toy models, I make a long tube or
Yes.
2 dimensions, a long channel, which sort of has a ratchet-like structure in it.
Okay.
Can this particle get in so that it has a positive velocity in one direction, or is it because it's the way it relaxes, it's always guaranteed that it diffuses?
It's always guaranteed it diffuses, I think, I would say. There's a question there. Yes.
Wave percolation just means percolation of the complement of the spheres?
Yep.
Great, thanks.
Yes. Or it's also, it's a Swiss cheese model also, or it's the, yes, it has different names, sometimes in mathematical literature, but yes. Anything else? Thank you again.